Our next session features Dr. Enrique Cuan, another research professor of the Institute, who will explore the design parameters and mechanical properties relationship with additive manufacture architected metamaterials. Thank you.
Okay, hi everyone. Let me start first with this advertisement of the group. This is a summary of what we do in the lab, some of our numbers, industrial collaborators, and so on. And this is what we're going to talk about. We're going to try to explain what a metamaterial is, why is it called metamaterial, then how do we get ideas to design them, why do we 3D print them, then some of the mechanical properties we have been able to understand so far. And I want to close my presentation with a special case. And before starting, everything that I'm going to present is because of these peeps here. Right. So in this slide, I'm showing how the property map of materials has been evolving through history, from very prehistoric times on the top left to some more recent times in the bottom right. And as you can see from this chart, the idea is that we plot a property on the vertical axis against density in this case. And the main objective that many demanding applications are actually waiting for us researchers to be able to come up with some solutions is to be able to fill the gaps in these material properties maps. And because of the inclusion of porosity in these structures or the materials, we are being able to cover some spaces in these maps that weren't covered before. How to achieve this? Well, the ideal material might be the one that is very light and with very high properties. So that would be one way of achieving this, could be considered by adding intended porosity to that structure or to that component. And you can achieve that nowadays, you can achieve that via two paths. One of it is through cellular materials, and one of a more maybe popular one might be using topology optimization. Issue with topology optimization might be that it ends up with very fashion parts. You see the geometry here, and I believe that the final user tends to be a little bit cautious on the employment of these parts because the final shape. Now, one step before employing topology optimization might be to explore the use of cellular materials, because at least they offer a periodic arrangement. And us as engineers, once we see something that is actually properly arranged, we tend to feel a little bit more secure. So a mechanical metamaterial is that if you consider a solid block and gradually you start removing material from it, and if you control the amount of material that you have removed and the shape in which these materials have been, the shape in which the material has been removed from the original structure, then you have come up with a metamaterial or cellular material, lattice material, foams, or other synonyms around. Metamaterials can be built from the repetition of unit cells. You have a small component, you repeat that through space, and then you come up with a cellular structure. More key concepts in this field could be volume fraction. How much material am I actually using within this structure? How do I test the properties? We are going to assume that the structure is continuous and homogeneous so that we come up with effective properties, because we are not creating a new material. We are creating different ways of distributing the material within the component. And another important aspect is deformation mechanism. These structures, they deform or they respond to loading in two main ways. The first one is the components respond by bending. So these are called bending dominated. The bottom ones, they respond by being stretched or shortened. So those are stretch dominated. This is a typical stress strain curve of a cellular material under compression. You can see it starts with a linear elastic response, then you have a roughly constant stress and deformation, and then it densifies. Advantage of this is that because of the plateau or constant stress region, you can obtain very advantageous properties in terms of absorbing energy. These are some popular examples. With the employment or the advent of additive manufacturing, these complex geometries have been able to be produced nowadays. Now, how do we create them in the lab? We like to play a lot with math, and you'll see why. We can use arcs or sections of circumference. We can follow trigonometric functions. The idea is to have a mathematical parametrization, because we know that every change in the geometry will result in a different mechanical property. We have also come up with a higher level of curve definition, like Bezier curves or fractals, or even a more complex approach to design metamaterials. In this case, we still have trigonometric functions, but we play on the way these are distributed in a plane, so that we come up with these surface-based structures. Now, I guess all of you are here because of 3D printing, so yeah, we 3D print these things, but let's see how it goes. These are some of the issues we encounter when we 3D printed by the commonly available FDM procedure. You know, this is a highly anisotropic process, so you need to be aware of that. You won't be able to fabricate sharp edges or sharp corners. Also, if the dimensions of the structures are so small that you need the extruder to move fast between 2 points, you may end up having this kind of defects. Now, what happens when you use stereolithography, which is based on liquid resin and an agent that is going to solidify the resin? Issues we have encountered here because of the geometries we are expecting to be fabricated. We have uncured resin, so you have unintentional porosity, and you can also have some extra material that wasn't be able to remove before these are cured. And all of those defects will add extra properties to the component. And of course, one big issue that I think might be now easily, or we're in the process of solving, is with approaches like Dr. Rafiq was presenting when you recycle the material. We have also come up with some metallic structures. Again, the issue of the supports, but I want you to look at the following slide. If you want such complex geometries, and if the process that you're going to use to fabricate them is powder-based, these structures have to start from something. It might be a single point, and if that point is not properly attached to the base, once the machine moves, it's going to be removed, because it will start with a very tiny little point. It won't start with a big part. So being able to produce these structures with such complex geometries still requires a lot of tuning or adjustment of the parameters. Now, some insights into the mechanical properties. Of course, we follow the 3 conventional approaches. Some of them are more popular than others. Some of them are more fun to see in the lab. First one, experimental, or in other words, brutal force. The way I see it, you break stuff. So you don't have to be falling in love a lot with your designs, because at the end of the day, you're going to break them. Computational approaches, you can run more combinations of parameters, even more than the ones that you're going to actually fabricate. And finally, some analytical approaches, which are probably the less popular, but probably the more insightful. Okay, what do we do when we are playing with experiments? For instance, these graphs show how the stiffness changes as a function of relative density or volume fraction. Okay? And you can see how important the role of the structure or topology becomes, because you see 2 ways in which the structures can respond. One of them has a macro buckling, and the other one has some micro buckling at the cell wall level, although both of them have the same amount of material. So you are not only controlling the overall effective property, but you are controlling how these guys respond, how these are going to be deformed. Like in this case, again, we have some buckling, but because of the fractal design, we can control when that buckling is going to stop using the same parametric definition of the curve. Now, this slide shows how important it is to be aware of the mechanical properties. Sometimes there are a lot of effort trying to come up with new materials, being able to process them using fabrication techniques. But we need to be aware of what's going to happen with the mechanical properties because, for instance, these structures show how the response changes once we change the orientation of the unit cell. So same unit cell, same material, same amount of material being used, just by changing the orientation, different response. And imagine how important it becomes when we want to launch this for biomedical applications. If you don't know that, you'll say, okay, it's cheaper or it's faster to fabricate the structure under this orientation, doesn't matter. Then you jump to the user sits down, and it not only compresses, but it twists because of the orientation. So once you play with orientation, you have coupled deformation mechanisms. You may want to expect the structure to respond by pure compression, and then it ends up twisting or bending because of orientation. This is the example of the structures we can create with complex mathematical representations. Look at all the possibilities we can have. And by playing with it, we can have different stress trace responses. We can have a response that it will always going to gain stiffness. And we can have a response more typical with the plateau region, ideal for energy absorbing applications. Jumping to computational approaches, for instance, here we can play with two structures that are going to have the same amount of material, but one of them is more sensitive to shear deformation. You know, in bending, there are two main deformation mechanisms, either by stretching or compressing, and by shear. One of those two structures is more sensitive, to shear deformation. You can control how much you want the shear to participate by adjusting, in this case, for instance, the amplitude of the trigonometric function that defines the metamaterial. Some other more complex loading scenarios, how the stress is distributed when these guys are loaded out of plane. Sometimes when the structure is designed in plane, we believe that it's only going to be loaded in plane. But what happens when these guys are loaded out of plane? How the stress is going to distribute? That's something in which computational approaches offer a wider range of possibilities so that we researchers can understand what is happening. Finally, the analytical approach. You may say, I don't want to see math involved, but sometimes it brings very useful insights. I believe that, for instance, if the structure, you are lucky enough that the structure can be analyzed analytically, and you can come up with an analytical model, it will bring a higher level of understanding of what's going on in terms of micromechanics. You cannot always do that. For instance, surface-based structures. Surface-based structures, if you want to understand them analytically, probably very complex. But these guys, you know, these are thin, these can behave as beams. You know, there's Castigliano's second theorem. I can understand how the energy participates in the deformation of these structures. And it allows you to, as I was saying at the beginning with the property maps, as I presented in the very first slide, you can see that we were able to cover some areas that weren't covered before, and not only cover them, but we know how each parameter actually participates in the effective mechanical properties. I know if they're going to be deforming mainly by bending, or by stretching or compression, or even by shear, because when the geometry of the structure becomes more complex, it's not a pure bending-dominated structure or a pure stretch-dominated structure. It's a combination of different deformation mechanisms that participate. Okay, and finally, the special case. It's very good that teams like Dr. Isaac was presenting in the I think it was the first presentation he covered. They are trying to print stuff that has some initial or intended curvature. Now, all the examples I have presented before are simple cubes. I have some in my bag. If you find me around later, I can show you. But there are simple cubes for mechanical testing. Demanding applications, airplanes, automotive, biomedical, they are not going to ask for a cube. They want something with complex shape. So the very first step to be able to come up with a solution using these approaches is to understand how these behave when the external geometry is far more complex than a simple cube. And the first step to achieve that is being able to fabricate them using additive manufacturing that is not following the conventional flat layers stack, but to make parts with a stack of curved layers, like the one you see on the right. And for that, we propose an algorithm so that you take the 2D version of the cellular pattern, project that on the complex structure, and then with machines that have a higher degree of mobility or more degrees of freedom, you can actually print these things. What is the advantage? The advantage of using such machines that don't only allow us to print flat layers? Well, one of the advantages is that we can create structures and ensure the continuity of the components that build up the structure. If you don't use non-planar additive manufacturing approaches, you can ensure that continuity. And if continuity is not there, properties go down. And I think I'm just in time to acknowledge some of the partners that we have been collaborating with, some industrial ones, some from government-based institutions. Some of the references I used, and that's it.
Thank you very much, Dr. Cuan. Here we have a question for you. Yes.
Yeah, thanks, Enrique. It's quite interesting. You know, in this kind of deformations, hysteresis is playing a big role when you are working in this dynamically. So, and I understand, even in your videos, that you are gaining energy in your system, right? If it is not recovering the entire form. So that could be a mess to work with when you are, you know, making cycles and cycles using this material. So how you are dealing with that?
It depends on the structure. Not all the structures are going to be ideal for every loading scenario. The structures we have characterized under cyclic loading, we have been able to tune the properties or the response so that that hysteresis is being reduced. So some structures resolve with more, some with less. The approach is that you properly pre-identify which one will be responding in the way you want. Some of them, you can deal with that, and those are not ideal for very dynamic loading scenarios.
Thank you. Dr. Dora, please.
Yes, well, first, excellent presentation, Enrique. And in one slide you mentioned, or what I saw that you mentioned about uncured resin. So I was wondering if do you think it is because maybe there is not like intimate contact between the two layers, and then you don't allow the reptation of these polymer chains through the two?
I think the uncured resin is mainly because we are not very careful with the post-process. We tend to think that once the printer is done, that thing is already to be used. But because of the sizes we are 3D printing the samples at, those sizes make very hard to remove the uncured resin. So we leave them there. That's the reason. It's because of the size, not because of the process. Same structure, same process. In a bigger scale, we might be able to clean it in a proper way, in a more proper way, before the curing process or the post-curing process. I think it's because of that.
All right. Oh, have you considered, for example, well, because I have done similar structures, and what I saw, like for example, if one layer has certain orientation of these polymer chains, for example, if you have more of certain orientation, it's more difficult to allow the reptation of this, to get the perfect welding.
Yeah, of course, orientation matters. Even from the manufacturing point of view, we have decided to use this orientation because it brings better results in terms of having a more homogeneous structure in the plane. If we change orientation, it might result in something different. But yeah, orientation matters.
Thank you for the presentation. I recently read a publication by the University of Zurich where the researchers used a scanning microscope to precisely place atoms to try and make a superconductor or possible superconducting materials. So I'd like to hear your take on the possible future of sort of atomic level structures for things like metamaterials.
Too small for me. The main idea behind metamaterials, and I try to give this message to others, is that the strength of our group is on proposing novel topologies, because we believe that we haven't covered the entire property space available, and that is because what do we print? A honeycomb. But honeycomb is not the only geometry we can print. Now, that is with the additive manufacturing capabilities we have at the moment. If researchers are working on a higher level of manufacturing approaches so that you can control the distribution of atoms or material at a more smaller scale, then possibilities are infinite. Yeah. Only with the scale we are working, we are already expanding the materials property chart. Imagine what we can do if we become smaller. So I like it.
Thank you very much, Dr. Cuan. Un applause.